Hello everybody, welcome to chapter 20. Now in this chapter we're going to be looking at submicroscopic, macroscopic connections. Okay, I do not hit a lot of the math in this chapter very heavily. I just want you to kind of come on board with some concepts as we start progressing toward heat engines. Okay, so heat engines are devices used to convert thermal energy of a gas into mechanical energy. So to be able to understand the limitations of thermal energy to work conversions and how we can try to maximize the conversion of thermal energy into work, we need to understand the submicroscopic behaviors of things that are in the gas phase. Our question really here is, excuse me, scroll this down. How does the submicroscopic world of gases relate to work and heat and processes at the macroscopic level? Okay, so first we're going to discuss what particles are doing in the gas phase. So gases are made up of atoms and molecules that are in constant random straight line motion. If we were to look more closely at this motion, we could ask, are all the particles moving at the same speed? The answer would be no. Are they moving in the same direction? The answer would be no. It's very chaotic. Okay? Now, they did experimentally look at speeds of particles. So if I have a source of particles and I let the particles pass through a slit, so we're letting through only particles that are traveling in this direction, okay? And we let them pass through here, and this device, these wheels turn at a specific angular rate. And there's a set distance between them. So if you let them turn at one angular rate, you can measure all the particles that have the speed to make it from one slit to the other in that time period. And by looking at that and looking at different angular rates there, we're able to see that if we have different speeds, okay, meters per second down here, and we look at the percentage of nitrogen molecules at 20 degrees C, we can see that there's very few of them moving between 0 and 100 meters per second, but there's some. Very few of them moving between 1100 and 1200 meters per second. And we have a nice bell-shaped curve here, a kind of bell-shaped curve. Now, it extends a little bit more in that direction, that's okay, but this is a bell-shaped curve. Okay? The most likely speed for a nitrogen molecule at 20 degrees C is between 500 and 600 meters per second. Now, this classroom right now is probably at around 22 degrees C, so the average speed is somewhere, let's say, between 500 and 700, probably a little bit, inch up a little higher. If we go to a higher speed, the higher temperature, the range of speeds over which the nitrogen molecules move would increase, and the percentage at each speed range would go down, and the most likely speed would go up. So for normal nitrogen molecules at room temperature, average speed 550 meters per second. The particles in a gas sample have a range then of speed, and the number of particles at a given speed gives a bell-shaped curve, and there's an average speed for the gas particles. As temperature goes up, like I said earlier, the bell curve gets broader and the peak moves up to a higher average speed. This tells us that speed is a measure, temperature is a measure of average speed at which the particles in a sample are moving. And since kinetic energy is 1/2 mv squared, then we can say temperature is a measure of average kinetic energy of the particles. Okay? So the macro property, temperature, depends on the submicroscopic property of speed of particles. So things like temperature and pressure macroscopically relate back to submicroscopic behaviors. Now, the particles are always moving. and they can encounter other particles, and they can encounter the walls of the container. Okay? We talk about the mean free path, which is the average distance a particle travels before a collision. The mean free path, of course, is going to depend on the volume of the container and the number of gas particles present and the radii of the gas particles. The more, when particles collide, they're going to change direction and or speed. Remember that on the atomic level, we consider collisions to be elastic, which means the sum of the kinetic energies before and the sum equals the sum of the kinetic energies after. We already know that momentum is conserved. Momentum before would equal momentum after. Okay? When they collide with the walls of the container, they will change direction but not speed. The collisions are elastic. Now, nitrogen molecules in this room, like I told you earlier, are traveling at about 550 meters per second. They're whamming into you at 550 meters per second. But they're so tiny that you don't feel it. You don't register it. It's kind of normal pressure. There are approximately 1 million collisions in this room right now per second. Okay? We can see that individual gas particles then are traveling, the direction of travel and their speed are rapidly changing if we're having 1 million collisions per second, and every collision produces a change in direction and or speed. Now, pressure. Pressure comes from the collisions of the gas particles in a sample with the walls of the container. And the average effect of the effect of adding up all of those collisions with time, okay, on the surface, which gives you a force divided by the surface area, is how you get pressure. Okay? For gases, average speed is very important. More precisely, root mean square speed, which eliminates the problem of direction of travel. So velocity equals Vx squared plus Vy squared plus Vz squared square root. Velocity average is Vx squared plus Vy squared plus Vz squared divided by the three directions. Well, let's say average of x plus the average of y plus the average of z. Okay, root mean squared is the square root of velocity squared average. I know that seems weird, but it's a very specific process of getting it. And the root mean squared is related to temperature and average kinetic energy of the gas particles. Okay? The translational kinetic energy of an individual gas particle is given by the following. I will make friends with this system. Nope. Nope. I will win. E average, K, is equal to 3/2 KB times T. Now, KB is Boltzmann's constant, T is temperature in Kelvin, and this E here is average energy. So the root mean square velocity is equal to the square root of 3 kb T over m, the mass of the particle. So notice the root mean squared velocity is related to temperature and related to mass of the particle. The more massive a particle at a given temperature, the slower its root mean squared velocity is going to be, its average velocity. Okay? Now, I'm not going to make you do any calculations with this. This means that temperature is a measure of average translational kinetic energy for the system. Okay? For a monatomic gas, the energy they possess is all due to translational kinetic energy. It is equally partitioned along motion along each axis. So, 1/3 of the energy is due to motion in the x direction, 1/3 of the energy is motion in the y direction, and 1/3 of the energy is due to z motion. Okay? Each axis is an independent way to store energy. So we talk about it being an independent mode of energy storage. Okay? When we have two or more atoms and we make a molecule, we add in vibrational forms of kinetic energy and potential energy. Okay? So we also then need to add in rotational kinetic energy. This gives us a lot more ways to store energy in the particles. Okay? The number of degrees of freedom, when we talk about degrees of freedom, it's not whether or not you got a test or not. The number of degrees of freedom of a system is defined as distinct and independent modes of energy storage for the system. For a monatomic gas, there are 3 modes of freedom, or 3 degrees of freedom. Okay? Because there are 3 modes of energy storage. Energy storage along the x-axis, a y-axis, and the z-axis. This tells us why there is not a difference in the heat capacities of monatomic gases, one from another, and why the heat capacities of diatomic gases are also essentially the same, because they're going to have the same modes of energy storage. Okay? So, atom I has translational kinetic energy. Its energy is E sub I, but no potential energy or rotational kinetic energy. So nitrogen atoms in a gas at a temperature T. So the thermal energy is the thermal energy of particle 1 plus particle 2 plus particle 3 for however many particles we have times the average thermal energy. All the thermal energy is the form of translational energy because there are no bonds, so there is no vibration, no stretching or compressing. E thermal is 2/3 N kBT, or 2/3 N RT, where N is the number of moles of gas particles. Okay? Change in thermal energy is 2/3 N RT delta T, or NCV delta T, where CV is that 3/2 R. CV is equal to 3/2 R, or 12.5 joules over moles Kelvin. So Boltzmann worked this out for us. Okay? Perfect. The equal partition theorem states that the energy should be equally partitioned between the 3 axes along which the particles can move. So again, reinforcing the idea that there are 3 independent modes of storing thermal energy and the degrees of freedom. Okay, I've already mentioned this, but one more time, hint, I might ask this on a test. Degrees of freedom, the number of distinct and independent modes of energy storage a particle has. For a monatomic gas, there are 3. Now, let's think about the diatomic gas from a classical physics point of view. In the classical physics point of view, we will predict 8 degrees of freedom. The motion along the x-axis, motion along the y-axis, motion along the z-axis. There is vibrational motion, there is rotational motion, and let's see, the 3, and then we've got rotational end over end, the z-axis, rotational end over end, y-axis, rotational motion along the x-axis. We have vibrational motion. Okay? We have all of these modes. We would see 3 rotational, 1 vibrational. Both have a potential of both a potential and kinetic energy, 3 degrees of freedom. That gives us an all of 8 degrees of freedom predicted. Through experimentation, though, we have discovered that there are only 5 degrees of freedom. Okay? We don't know which of the degrees of freedom are missing, but we know experimentally there are only 5. Now, this shortness on our degrees of freedom for a diatomic gas is an indicator that Newtonian physics really doesn't hold very well on the atomic level. And this was another push for quantum mechanics, okay? Trying to explain the world of the itty bitty. So, it turns out that C sub V for a diatomic gas is 5/2, 5 degrees of freedom divided by 2, times R, or 20.8 joules over mole seconds. Remember that for the monatomic, it was 3/2 the degrees of freedom. An important result of quantum mechanical statistical approach to gases is that the energy of the system of particles is equally distributed among all the possible energy modes of storage. So let's think about thermal interactions of gases, because thermal interactions are going to be something that's going to be very important as we look at heat engines. So let's think about a box with a thin membrane that separates the 2 sides of the box, and we have gases at 2 different temperatures on each side. Okay, so it's insulated here around the outside, and I have this very thin membrane. And I have system 1 at T1 and system 2 at T2, and I have N number of gas particles on this side, N2 gas particles on this side. Okay, roll this up. And I have a thin barrier. Okay, so particles can come up to this barrier, they can both be running at that barrier, and they can collide. Let me see if I've got a picture here of that. Yeah. So a fast-moving particle here, slow-moving particle here, they collide at the barrier. The barrier allows them to collide with each other, but doesn't allow the particles to move from one side to the other. At this collision, one of the things that happens in any collision is during the collision, the fast particle is going to lose some energy and it's going to move away going slower, and the slow particle is going to move faster. So there's a net flow of energy from this side to this side. Now, every time there's a collision at this membrane, okay, sometimes it can be a fast-moving particle from this side and a slow-moving particle from here. Sometimes it's fast here and slow here. On average, though, in the beginning, these particles on average are moving faster than these particles. So the collisions at the wall are going to happen for the most part with energy moving in this direction, because these guys are moving faster than these. Over time, then, the energy over here, average kinetic energy, is going to come down. Average kinetic energy over here is going to go up until they reach the same average kinetic energy. And then, for every collision where energy is going this way, there'll be a collision with the energies going that direction, and they'll reach thermal equilibrium. So every collision is an energy exchange event, a thermal energy exchange event. When a lesser energetic particle collides with a more energetic particle, we always trade from lesser to more, from more to less. Okay? So even though each collision is an individual event, there is an overall theme to the way the energy is going to be transferred. So if we look at the sum of the internal energies of the 2 systems before interaction and after interaction, the sum of the energies of the 2 systems, because they're in isolation, would have to always add up to be the same. But some energy is going to be lost by system 1 and gained by system 2. There is a net flow of energy from one side to the other until they reach thermal equilibrium. Now, once they reach thermal equilibrium, does that mean no energy is being exchanged? Okay, I said it earlier, no. It just means energy is being exchanged at an equal rate. So, when I put something hot next to something cold, why doesn't the hot get hotter and the cold get colder? Because when collisions happen, we always see energy move from the object that's moving faster to the object that moves slower every time. So even though each individual collision is its own energy exchange with its own direction, we'll see a net movement in one direction of flow of energy. The transfer of energy from hot to cold is an irreversible process. That means that it happens spontaneously in one direction and one direction only. It does not mean that it cannot be reversed, but it will not reverse spontaneously. Okay? The transfer of energy is an irreversible process, which means that it happens spontaneously in one direction and one direction only. Okay? Now, let's think about the why. And think about some things that we know are irreversible. Mixing cream into coffee, or a car crash into a wall. Okay, you recognize an irreversible process by thinking about watching a film running in the forward direction and running in the reverse direction. So think about watching cream being stirred into coffee, and if you watched it in reverse, the film, you would recognize immediately that I couldn't stir coffee and get the cream to come out of it. Okay? You can tell the difference in the forward and the reverse direction of a film if it's an irreversible process. Now, if I were to watch two pool balls colliding in the middle of a pool table, I just saw them come in and collide and bounce off. If you ran that film forward or backwards, you couldn't tell by looking at the film whether you were watching the forward direction or the reverse direction. So, individual collisions, which are reversible, you can't tell the difference between forward and reverse, somehow lead to a macroscopic process that is irreversible. Okay? So when we're thinking about submicroscopic processes, we're talking about huge numbers of collision events. So we're talking about the statistics of large numbers. Now, if we were to have a ball here of containers, a container of balls labeled 1 through 20. Okay, and I started out with all the balls in beaker number 1, and I started trying to move them to beaker number 2. So I had all 1 through 20 here, and an empty beaker here, and I had a deck of cards labeled 1 through 20, and I drew the first card, and it said move ball 1. And then I shuffled it, and I drew a card, and then it said move ball 3. So if I went through that deck drawing cards enough, what we'd eventually see is I'd end up with 10 balls in beaker 1 and 10 balls with beaker 2. And they would be randomized, okay, what numbers were in what beaker. And if I just kept going it would essentially stay that way. Each draw is an individual event and things could go either direction, but is vastly more likely to have the 20 balls separated between the two beakers than it is to have all of them in one beaker or the other. So reversible submicroscopic events lead to irreversible macroscopic processes. Okay? It's vastly more probable than the other. This brings us to entropy. Okay? Now, entropy is the enemy of taking all of the thermal energy and getting it converted out as work. Okay? Entropy is the reason we can't do it. Entropy is the measure of the probability that a macro state will occur spontaneously. Okay? It's a measure of the probability that a macro state will occur spontaneously. An ordered lattice, solid phase, has a very small probability of occurring spontaneously. There are very few ways that you can order the particles in the solid phase in a crystal lattice. Whereas a random arrangement is much more highly probable because there's more ways for the particles to be arranged randomly than there is in an orderly fashion. So if we were to look at figure 20.18 on page 563 in your textbook. Okay, I'm going to shoot it up on the screen here so you guys can see it. Okay guys, if we look at this, okay, just thinking about having particles nice and lined up, a little bit more motion, more erosion. We have an increase in randomness, an increase in entropy, an increase in probability. If I had gas particles, it's much more likely that they're going to be like this than in that nice ordered pattern. Is it impossible? No, but it's much more likely to be this way. There are many more ways that I can have these individual gas particles spread in here randomly than there are ways that I can have them in nice lined up rows. So when we're thinking about the system, okay, then that's what we're thinking about. Now, okay, your book brought up some other images. Think about tossing coins. You know, is it, if you had a whole bucket of quarters and you toss them up in the air, is it very likely that when they hit the ground, they're all going to land head up? Okay? If I toss them in the air and I let them hit the ground, it's more likely that I'm going to have part of them heads up and part of them heads down. It's just more likely, more probable. All right, now, this brings us to the second law of thermodynamics. The second law of thermodynamics says that the entropy of an isolated system never decreases. The entropy of an isolated system either increases until equilibrium is reached, or if the system is at equilibrium, it stays the same. We can then go and say when two systems of different temperatures interact, heat energy is transferred spontaneously from hotter to colder object and never from colder to hotter. Okay? Lastly, entropy can be defined as the time direction in which the entropy of an isolated macro system increases is the future. So the direction of an isolated system's increasing entropy is the future. And this, guys, brings us to the end of chapter 20. No math, just some concepts. Okay, that's where I'll stop.